All right, so section 8.2 here today. We're looking at applying transformations to this logarithmic function that we just discovered in section 8.1. Well, these transformations are the same transformations that we've been applying all course, right? That is when we're looking at our A, K, P, and Q values in order to find our vertical and horizontal stretches and reflections and compressions and translations. Okay, so now in terms of the locations of these values inside a logarithmic function, it looks just like what's written here. You'll notice I added in these square brackets. They can help simplify it for you. Nice and easy. Our A term, that is our vertical stretch or compression or reflection, that can be found on the outside of our function, which makes sense because it works vertically, multiplying by our logarithm. Okay, our K value, which is, again, our horizontal stretch or compression or reflection, can be found inside the logarithm, multiplying by the x. Now, K should always be factored out away from your p-value if you're going to find each of these values here. Your p-value can be found inside the brackets if there are any brackets there. Subtracted from x, so we'll need to be careful. Since it's subtracted, we need to change that sign if we pull it out of this function. And lastly, our q value, again, on the outside of our logarithm function, which makes sense because it's a vertical transformation just there at the end, or it could be found at the beginning of the expression as well. Now, before we get into that, though, that was, I guess, a little bit of a head start. Before we get into that, though, let's take a look at some restrictions that we might find on these logarithmic functions. Okay, so I encourage you to pause the video here and consider for A, B, and C, consider writing these in exponential form. Try to find why it is there are no solutions for each of these expressions. All right, the first one here, if we put this into logarithmic form, that is a base of 2, and it's an exponent of something, an unknown exponent, needs to equal -8. Well, if we think about that for a moment, 2 is a positive number. No matter how many times we multiply 2 to itself, by itself, we will never get a negative result. So we cannot have here a negative result to this problem. Therefore, there are no solutions. No matter what x value, this equation will not be true. All right, let's look at B. Again, we can write this in exponential form. Okay, so a -2 is the base. There's an unknown exponent, and it needs to equal 8. Well, no matter how I apply my exponent here, I know that -2 to the power of 3 equals -8, or I know +2 to the exponent 3 equals +8, but there's no way to find a -2 base with an exponent to equal a +8. So there are, again, no solutions. All right, right here, the problem, the issues arise from having a negative, we call this a negative base to our logarithm. In part A, the problem arose because we had a negative, what we call argument to the logarithm, and that is the piece inside the logarithmic expression. And lastly, let's look even further. Okay, well here we should have a base of 0, an unknown exponent, and it needs to equal 8. Well, we can see right away, no matter what our exponent is here, the left side, the left expression, will equal 0. So therefore, there are going to be no solutions. So the problem here is that our base is 0. Our base cannot be 0 if our argument is anything but, right? So we can assume that it's never going to be useful to us to have a base of 0. All right, now our conclusion here is that our logarithms of the form log base A of B, so again, A is the base, B is the argument, can only be evaluated if we have A greater than 0, that is our base is greater than 0, and B greater than 0, that is our argument greater than 0. Okay, so our base and argument, I didn't plan this part of the note out very well now, did I? We can move that label down here. Our base and our argument must both be greater than 0 in order to work with here. All right, now I've already gone over this A, Q, P, and K in order to work with. This is a refresher of our mapping rule. If you're a little bit confused by that, you can look back to section 1.4. Once we have our A, Q, P, and K values, I'm sorry, I know I said those out of order. Once we have those values, then we're able to build our mapping rule. Then we're able to map any transformations. Or if you choose to map without using a mapping rule, you can map it by its, you can graph a transformed function by its transformations, just like we learned in, let me see, I believe that was chapter 3. You can graph by their transformations. That would be accepted as well. You just need to make sure that you are showing your work. All right. Now, something that we should be aware of, a little bit of an aside. If we have a log expression looking like this, there's something that's missing. Right? It's missing its base. There's no base in there. Well, you'll notice sometimes through convention, and I know we spoke about this a couple of weeks ago, through convention, if I have A, then we assume there's a hidden exponent 1 on that A. If I have a root of A, I assume that there's an index of 2 on that root. I assume it's a square root. It's not a cubic root. It's not a quartic root. It's not a quintic root. It's a square root, right? So when we're working with logarithms, then if there is no base, then we assume the base equals 10. All right, so we should be ready to handle that in this chapter for any problems moving forward. So here we know, okay, so f at x is the log of x. Sorry, so it's just a base logarithmic function. All right, so if it's a base 10, then we can already know of 2 points. All right, so a base 10, we know of 2 points. If we have the base 10, we know the 10 to the exponent 0 will equal 1. Okay, well, that's great. That means that where x equals 1, y will equal 0. All right, I also know 10 to the exponent 1 will equal 10. Okay, great. So that means where x equals 10, y equals 1. We call these two anchor points. Okay, no matter which base we're working with, if we consider the exponent 0, exponents 0 and 1, then we can very quickly find two points that we can work with to graph our function. Okay, so again, anchor points at 0 and 1, and that is we're working to find where y equals 0, and we're working to find where y equals 1. Okay, so there are unknown x values there that we're filling in the blanks for. We'll call them x0 and x1. All right, now we know through our exploration yesterday, we also know when we're working with a logarithmic function, we can expect a vertical asymptote. In this case, we're going to have a vertical asymptote at at x equals 0. And the shape of our function will be something like this. All right, so when we apply transformations, we're going to be applying the transformations to this base function that we're sketching out with the asymptote and with 2, again, we call them anchor points. We've used the idea of anchor points before if you're graphing a quadratic or a cubic using vertex form, but I'm not sure if we've necessarily called them anchor points in this class. All right, so we can push forward. Now here, judging by this form right here, this is where you'll want to be referring to if you're trying to figure out which transformations are being applied. Judging by this form right here, we can see, and I'll write this, you know what, I'll take a copy of that down below. F at x equals a times, nice and easy, f at x equals a times the logarithm of k times x minus p plus q. All right, so that's what we're going to work with, and we need to try and find out which values we're working with. Okay, so we can see right here, we can come up with an equation that looks just like that if a equals 4 and if p equals 2. Is that right? No, it needs to be a negative 2, right? We need to change that sign because p needs to be subtracted from x. Okay, so here there are only two transformations, and that makes sense. We see only two numbers here. So we're working with a vertical stretch by a factor of 4. And we're working with a horizontal translation two units left. Okay, so here if we choose to graph this by transformations, we can graph our base function. I'll graph that one in red just like I did up above, where I can use those two same points coming from, and we can write them out right here. 10 to the exponent 0 equals 1. 10 to the exponent 1 equals 10. Okay, so I remember my y values are the exponents. My x values are what they equal. Good, so I'm working with 1, 0, and I'm working with 10, 1. This was my base function. I need the vertical asymptote y equals 0. My base function looked something like this. I can plot that y equals log x. All right, now I can apply these transformations in order, so I need to work with a stretch or compression first. So I'll work with y equals 4 times the log of x. All right, well then I'm vertically stretching everything by a factor of 4. So if I take this point and I vertically stretch it by a factor of 4, it stays in the same place, right? A vertical stretch of 0 by 4 equals still 0. Now a vertical stretch over here, this is where the change happens. A vertical stretch of 1 4 times equals 4. So I'm looking at a new shape, something like this. And then I can apply as well. Lastly here, I can apply my horizontal translation 4 units to the left. 4 times the logarithm of x plus 2. Sorry, 2 units to the left, is that what I said? So everything gets translated, each of these points gets translated 2 units to the left. And I should have as well vertical asymptote that gets translated 2 units to the left. So that's at x equals 0. Oops. I can plot it. Let's try going from this direction a little easier. There we are. Now this, again, this was graphing by transformations. Graphing by transformations. But I know some of you prefer to graph by the mapping rule. So let's work with the mapping rule down here. Again, we can take our general transformed version of a log function here to work with, and I can come up with the transformations that are being applied. Or rather, I come up with my a, k, p, and q values, right? So here, a equals 3, k equals 2, p equals positive 4 here, and q equals 0. There is no q value. Okay, so that means my mapping rule, x, y, transforms to x over k plus p, a, y plus q. All right, so that means I'm working with x over k. Well, k equals 2, so x over 2 plus p, so that's plus 4. A here is 3, y plus q, which is 0. Right, so here's my mapping rule for this function, x over 2 plus 4, 3y. Now, again, I can plot the 2 points on my original function here. Same 2 points as up above, that is 1, 0, and 10, 1, with a vertical asymptote. Sorry for the bell there, folks. And then I can input these 2 points from my base function, which again, these 2 points I'm working with, okay, so that's 10 to the exponent 0 equals 1, 10 to the exponent 1 equals 10. So these 2 points that I'm working with are going to be 1, 0. I'll see how that transforms. Okay, well, that's 1 over 2 plus 4, 3 times 0. Right, so that means 1, 0 transforms to what looks like 9 over 2, 0. And my other point, 10, 1, transforms to 10 over 2 plus 4, 3 times 1. Okay, so that means it transforms to 5 plus 4, that is 9, 3. All right, so my 2 new points, nice and easily here, just trying to finish this before the office fills up here. We're working with the point 9 over 2, 0. Okay, so that's 9 over 2, that's 4.5, 0 right here. And I'm working with the point 9, 3. I can see that the horizontal translation here that I'm working with was 4 units to the right, and that means that I can expect my new vertical asymptote to be 4 units to the right. That is now at x equals 4, and my graph comes together like so. So at this point, you should be able to handle the rest of this note on your own. Try graphs D and E on your own, and then get into the homework.